Okay, so what I have for you today is just as usual. So we'll do one exercise to review what we did last time. And the topics that we discussed last time was mainly about flux. Okay, so we were talking about how can we visualize it's the electric field lines. So we quantify those lines in terms of electric flux, and it's linked directly to the strength of the electric field. Okay, so that's good. So we're saying that okay, if you can figure out the density of lines, that it means it's a line per unit area, that should directly tells you what is the magnitude of the electric field, right? So that was it. So we were saying that the way that we define this one, so it's simply saying that E can be found from the flux per unit area. That was the initial concepts that we started out. And then what we did last time was saying that, hey, because electric field is a vector, and then we can treat the A to be vector as well. So by doing this, now you can determine the orientation of the surface area and the direction of the electric field. So we came up with the way that we can define, or not, I mean, not define, sorry, the way that we can calculate the amount of flux through any surface area by doing the dot product between the electric field vector and the newly defined area vector. Cool? All right, so that's what we did last time. Is just saying that, okay, Ajahn, if you have a way that you can figure out the angle between the area vector and the electric field vectors, so it's just a dot product between those two, because if you know those two vectors that are parallel to each other, that is a guarantee that the electric field is actually piercing through that area in a perpendicular fashion, because the way that we define the area vector is by having that direction of the area to be perpendicular to the actual area. Cool? All right, so that's what we did last time. So let's apply that one more time here. And let's say if you can come up with, intuitive idea of what is that dots product is trying to do, and what is the flux calculation in some maybe more complicated shape. Now take a look at this. You have a cone with the base radius r and the height h, and is located in on a horizontal table. So now you have a uniform horizontal field piercing from left to right. Cool. Determine the electric flux that enters the left hand side of the cone. What do you think about this? All right. So they only care about the left hand side. So let me sort of like split this in half. Okay, so you have a left side and a right side. So let me sort of split this in half here. You only care about the left side though, right? So we can discuss about this one. If I'm asking you about, hey guys, what is the net electric flux through this closed cone shape? You will say zero again, Ajahn. The reason is because the flux that enter the cone, it's they all leave the cone, exit the cone on the other side. And because of the uniformity of this electric flux, the amount of flux that enter the cone is going to be the same as the flux leaving the cone, right? So that means there will be no net flux. So that's no big deal. But Ajahn, if you want to figure out the net flux, it's guaranteed to be zero. There will be no net flux through the bottom surface of the cone. No problem, because there's no penetration through the bottom. So that's easy. So you only care about the left hand side surface and the right hand side surface. But this particular problem is focusing on, hey, I only care about the left hand side of the cone. How much flux is entering? Even though we already knew that the net flux is going to be zero. What do you think, guys? Well, John, well, we can do just like what we did last time. You have to figure out the area vector first. And once you have that, then we can determine the angle between the E and the A, and then you do the dot products, right? But then when you look at this geometry of the cone, it's like it's not easy. The reason is because the surface of the cone here if you define this piece of area, and then you have, okay, let me call it a dA, a tiny piece area vector, dA. It's going to point perpendicular to it. That's no problem. But then if you move around this surface, the area vector is going to point like pretty crazily all in all direction, right? I don't know if I draw this one in perspective way correctly or not. Okay, let me try. Let me try. Okay, so it's go like this, go like that, like that, like I don't know, is it good or not? Yeah, but I hope you can see it. Does that make sense? All right. But anyway, the area vector supposed I don't think the angle is correct. Okay, sorry. That's not good. That's not good. It's supposed to go like this. Okay, like that. I think that's more like it. Here we go. There you go. All right, that's better. There you go. Behind. Let's go behind. There you go. All right. So the area vector is going to point perpendicular to the surface of the cone. But then your job is going to be a lot of trouble to try to figure out the angle between E and that area vector at particular surface points, right? At particular point on the surface. So how are we going to figure out the flux through the left side of the cone? What do you think? So I think this is going to be the core understanding of the whole thing that we are trying to do here. There is a meaning of the dots products in this particular sense of like something going through surfaces. So come back here, guys. So remember last time that we did this problem here? When you were trying to calculate the electric flux through the slanted surface, remember this one here? Yeah, the slanted surface here. You say, okay, the area vector is going to point perpendicular to it, so it's no big deal. And then you say, okay, electric field vector is going to point horizontally. You can determine the angle easily in this case. But by doing the dots product, you take just the horizontal components of the area vectors, right? So that means what you have to do last time was like, okay, Ajahn, I only care about this component here. This is what you care about. Okay. And it turns out when you were doing this, at the end, the area that you have to calculate turns out to be just the vertical area of that area vector. You guys with me here? Okay, follow my black arrow here. The black arrow here is just the horizontal component of the blue vector. But we already said the area vector pointing in any direction, it means the actual area must be perpendicular to it. So what you can think of this one is like here, the blue is the slanted area, right? But the black is the only component that you really care about in your flux calculation. But now you think about it, how can you get to the black area from the blue area? So the way that you can do this is, imagine this, guys. If I have a flashlight and I shine the light in the direction of the electric field, okay, so it means I'm going to shine the light horizontally. The blue area will cast a shadow as the black area if I put a screen behind this. Let's say if I have a screen behind this. You guys with me here? So that means it turns out the blue slanted surface will give you the shadow, okay, by shining the light in the direction of the electric field. The area of the shadow is the component that is perpendicular to the light. Make sense?
Okay.
Right? The shadow, it must be something that's perpendicular to the light all the time. So that means the shadow, the area of the shadow is automatically give you the component of the area that is perpendicular to the beam of light. Does this make sense to you? Right? So what I'm trying to say over here is the dots product, when you apply it to an area like this, is the same thing as you trying to do like an E on the area that is parallel to E, right? Or if you talk in the actual area, is the E that is perpendicular to the area. But when you say perpendicular, it means you only care about the, here we go, projection. It's just the projected area of whatever the piece of area that you're talking about. Does that make sense? Okay. It might make even more sense. Come back to this one. So think about this. So I'll do the same thing here. If I shine a beam, there's a beam of light pointing in the same direction as the E, because E, that is the electric field direction that we care about, right? And if I shine the light through this cone, and if I have a screen waiting for me, the screen is, of course, is going to be perpendicular to the beam of light. What should be the shape of the shadow casted by this cone? Well, John, I will get a triangular shape shadow. You guys with me? It's the same thing as this shadow over here. Does that make sense? So imagine this. No matter what, I mean, the left-hand side surface of the cone is going to curve, it's going to go crazy, whatever. But eventually you're going to do the dot product. So when you want to do the dot product, it means you only want the electric field vector to be pointing in the same direction as the A vector. So that's why you don't care about the slanted surface, some angle surface. I don't care. You only care about the surface that gets projected already onto a surface that is perpendicular to the E. So that's why it's the same thing as you only look for the surface that is coming from the shadow of that area. Does that make sense now? So that means what I want is, okay, flux on the left hand side of the cone is E dot, okay, I have to do some, calculus here a little bit because the A is not pointing in the same direction anymore. But what you know right now is the E times A perp. See, so now we get back to the original description of it's going to be electric field multiplied by the area that is perpendicular to the field. And now we know this is the projected area. And it's just a circular, I'm sorry, it's a triangular shape. So that means it's just going to be E, okay, times the area of this one. Okay, but John, that's easy. The base is 2R. The height over here is going to be H. So it's going to be half the base times the height. That is the area of a triangle. And that's it. So the answer of this one is ERH. But wait. One more. But Ajahn, yeah, projection is fine, but you forgot about the direction. Don't forget that we are still talking about the area vector. So in this case, even though you already projected, you already get the area of that, left-hand side of the cone. But when you look at the overall direction of the vector of that left-hand side of the cone, it's actually point leftward. Is that a word here? It's point toward your left. So when you already projected that area onto a piece of the screen over here, now it's like an open surface. So actually you still need to say, hey, you care about the left side of this one. So that, let me call this A left, perpendicular. So that is A that is perpendicular to the electric field, but it's on the left side of the cone. So that means overall, the angle between E and the left side surface area is 180 degrees. It's going to be cosine 180 right here. You guys with me? So it has to be negative flux, which makes perfect sense because flux is entering the cone. So we already agreed last time. If electric field is trying to enter the closed surface, it's a negative flux. And then you can imagine if this problem asking you the flux on the right-hand side of the cone. It's going to be exact same value, but it's going to be positive because you only care about the right side of the surface, which once you project that, it's going to give you the same triangular shape shadow, but now you care about the vector that is pointing to your right. And that's why if you find the net flux, it's going to be 0 because one is in, one is out, one is negative, the other is positive. They're going to cancel. And that's it. It's done.
Okay.
Negative H. Does that help? So this one is sort of like give you, I don't know, it's called more intuitive sense or not. So I can give you one more example, and I hope this will help. So let's say, look at my face right now. Okay. So this one might be better if we do in class. But imagine that if through, I mean, throughout my face here, if I have an electric field going, piercing through my face right now. Okay, think of it that way. Piercing through my face. So, and if I'm asking you, hey, but guys, I would love to find the flux through my face. It's gonna be like, Ajan, it's gonna be crazy calculation because my face, the surface area of my face is gonna point in crazy direction, right? But at the end, now whatever you get is going to be the same as the electric field multiplied by just the shadow of my face. If I have the screen behind me, you guys with me? So you don't have to care about the shape of my face whatsoever. You can think of this, the whole face of mine is just like a 2D, two-dimensional area. You can just, cut my face and then flatten everything, paint black, and that's it. That is the shadow of my face. So you take that area of my shadow, multiply by the electric field. That is the magnitude of the flux through my face. Does it make sense? Okay.
Okay.
And then, of course, Bajan, because flux is entering, right? It's get into my face, into my brain and everything. So it's going to be negative because even though you already flattened my face, put everything, paint everything black, turn it into just a shadow, but my area vector is still point towards you. So it's opposite to the electric field, something like that. All right. So that's what it means. So the shadow casted in the direction of the E will give you the projection, right? It's projection of the area, and that area of that projected, the area of the projected area, projected surface area will give you the value of the area that you need to multiply by the E to get to the flux. And that is a guarantee that the E is already pointing perpendicular to the components of the area that is, already projected already. I'm just talking in circle here. All right. But anyway, so that's why sometimes the dot product or every time that you have to deal with the dot product in mathematics, sometimes they call it a projection operator. Because if you interpret that dot product based on, you're dealing with geometry of a surface, then it's the same thing as you do the projection of that surface onto something or some screen that is perpendicular to another vector, something like that. Okay, does that help? All right, I hope it's sort of like maybe still confusing a little bit, but I hope it's just something that allow you to, have something in your mind for you to think about every time you do the dot product here. All right, guys. So that's it in terms of the flux calculation. So as I already said last time, okay, once you understand how to calculate flux, Gauss's law is simple, guys. Seriously. And you will be amazed how simple it is. So let me ask you this. So if, get back here, okay, almost done, guys. I hope I'll try to make this like as natural as possible. So remember this one here? We were talking about a spherical shape surface here, right? And then you say, hey, there is electric field line piercing out. And we discussed last time that the net flux throughout this sphere is positive, right? Remember that, right? Because the area vector is pointing out. Electric field vector is also pointing in the same direction. So the angle between those two are zero. So you always get positive flux. Or intuitively, electric flux is leaving the enclosed volume. So you get a positive flux, right? So let me ask you this. If you already have an evidence saying that there is a net positive flux through this closed surface, where does this come from? One more time. if you already have an evidence saying that, hey, Ajahn, within this sphere, okay, and when you look at this on the surface of this sphere, well, Ajahn, I found out that there is total net flux throughout this surface to be positive. So it means you already found out that net electric flux is positive. So it means electric field is just, piercing out of this sphere. My question is, where do you think this flux comes from? Does that make sense?
Okay.
Say, if there is electric flux coming out of this sphere, there must be a source that generating these electric field lines or these flux. So that means if you have a net positive flux, that leads to the conclusion that inside this sphere, there must be a net positive charge on here as well. Because we already said positive charge generating the electric field lines that coming out of it. It's piercing, it's pointing outward from a positive charge. So that's it. So if you said the net flux is positive, it's a clue telling you that the net charge must be positive in there as well. Does that make sense? Here, next one. These two examples give you zero net flux. When you said, Ajahn, there's no flux throughout this closed surface whatsoever, that is a clue telling you that there must not be any net charge inside this closed surfaces as well. Cool? So that's how easy it is. So the reason that we're trying to understand how to calculate flux on any closed surface, just so we know that should there be any net charge inside that closed surface or not. And that is the Gauss's law. Guys, we are done here.
Okay.
See, this is the flux calculation. We already learned it's just E dot dA integrate everywhere throughout the closed surface. Whatever this flux that you get, it must be telling you the amount of charge included inside those closed surface. And because to make units sort of like coincide with everything that we have learned, SI system and on, so now it's time for us to introduce a constant, because we didn't introduce any constant when we were defining flux. So that's why we need it now. Then we cannot avoid it. So that's what it is. So that's it. So the key concept about this one is, if you know how to calculate flux, it will lead you, or that is the clue, the big evidence telling you that how much charge should it be inside that closed surface. The constant is here just to make things perfect in everything else in physics. That's all. And that is Gauss's law.
Okay.
Okay, let me test your understanding right here, right? Just to make sure. Yeah. So let's say you have a charge Q at the center. Everyone knows that now electric field is supposed to come out of it. No problem. Let's say if I have three surfaces, S1, S2, and S3, in like a different shapes. S1 could be a sphere. S2 could look like a, I don't know, like a bacteria, amoeba, whatever membrane. S3 is a little bit bigger. Which one will give you the highest amount of flux? The answer is they must be all the same. Because, I mean, for this one, if I count, it's going to be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Of course, it's not a real numbers. But I mean, what I'm saying is, whatever the amount of electric field lines that coming out of this Q, no matter you're looking at, no matter which surface you're looking at, S1, S2, or S3, you will count the same amount of electric field lines, correct? So that means they are sharing the same numbers of flux. So that's clear. There's no problem. But now when you look inside these three surfaces, Ajahn, that's one Q right there. And that's it. It's done. So this means the amount of flux through these three surfaces must be the same because they have the same amount of charge in there, which is Q. And by Gauss's law, you can even tell the total amount of flux, net flux through these three surfaces must be Q over epsilon naught, and you are done.
Okay.
Isn't that cool? Look at the next one here. If you place the charge outside the closed surface, charge is outside. So it means there's no net charge inside this closed surface whatsoever. I can tell you right away, the net flux must be zero because there's no charge inside this closed surface. That's easy. It is that easy. I'm serious. That's it. Okay. That's how easy it is for you to link from flux calculation to the Gauss's law because charge is the one who's generating the flux. If you know the amount of flux through the closed surface, it will give you the net charge inside that closed surface as well. Okay, one more time. Try again. The figure shows in cross section. Okay, so think of it in 3 dimensions, right? So you have two Gaussian spheres. So every time that you're talking about the Gauss's law and you generate like a surface, and the surface is going to be used for Gauss's law calculation, so they put like a Gaussian adjective on top just to say, hey, so we're doing something under Gauss's law. Okay, so if you pick a spherical shape surface, you can call it a Gaussian sphere, so it's no big deal. If you pick a cubic surface, then you can call it a Gaussian cubes. All right, so that's fine. So now you say you have two spheres wrapping this positive Q charge at the center, and you have two cubes wrapping around this charge at the center as well. So rank the net flux through the 4 Gaussian surfaces. Which one will give you the greatest amount of flux? You guys still with me today, right? Okay, so the answer is okay, they're all the same. Why? Because these 4 surfaces wrapping this charge positive Q inside. So the net charge that is included inside these closed surfaces are Q. So I can tell net flux is Q over epsilon naught. And because the charge is positive, I put positive in there. And that's perfect. When you have positive flux, what does it mean? It means electric field lines is coming out of the closed surface. Easy? That is easy. Okay, one more time, one more time. Okay. So don't worry about this one yet because eventually we're going to do a lot of Gauss's. I mean, not a lot, but I mean, there will be some application of this one, but I already guaranteed to you that application is pretty limited. So you don't have to worry too much. But when we try to put it in like a general sort of like rule of thumb and all the stuff, it looks complicated. So when you see a real example, it's much easier, right? We can come back to this summary of application of Gauss's law after we have seen many examples already. All right, try this one, guys. So I'm gonna, instead of going through this slide, so I'm gonna do this. I'm gonna start blank and walk you through this one together. Okay, come with me here. So now I have a positive charge, okay, at the center plus Q. It's just blank. I mean, blank space. There's nothing. It's just here. And let's say about Ajahn, I am standing right here. Let me call it point P. And at that point is at a distance R away from the charge that I'm looking at. If I'm asking the same question, but Ajahn, I want to figure out the electric field at point P. We already learned that you can do that through the Gauss's law. I'm sorry, the Coulomb's law. It's a K Q over R square, right? So this one's checked. We learned that before. And we had the connection between this and the Coulomb's law and everything. So that's fine. But then I said, I'm going to do a different thing. Instead of using that Coulomb's law, I'm going to do this. Because this positive charge is just like a point charge. It's like it's a dot. It doesn't even have like a size. It's a dot in space. So that means electric field supposed to come out of this one in all direction. Okay, you guys with me here? Because if you close your eyes and imagine that this is a single charge, positive Q charge in the universe, this charge cannot tell which one is up, which one is down, which direction is north, south. There's no north, south, east, west. There's nothing. It's just like blank space. So when it has a blank space and it can't even tell which up, which down, which direction is which, it has spherical symmetry. You guys with me with that? Because I mean, when you look around, they all look the same to you. So that is a hint saying that electric field coming out this one is supposed to go out in all direction uniformly. And that spherical symmetry lead to a spherical shaped surface that I would love to pick it to be a Gaussian surface. You guys with me now? So your Gaussian surface now is your imagination. You're just wrapping around this positive Q charge using your own imagination that, okay, I have my own sphere now. And this sphere is our imaginary sphere. That's we're going to call it Gaussian sphere. No big deal. That's just a name. Okay. That's a Gaussian sphere or Gaussian surface. And then now we're going to apply the Gauss's law on this spherical surface here. So what I'm going to do is I'm going to calculate flux on this sphere. And we already said it's a E dot dA throughout the sphere. So I put a circle sign on it. It's a closed surface, right? And we said every time that you want to figure out the area vector, you just slice this into a tiny piece. The area vector will point out in the radial direction because this piece is a tiny piece. So I'm going to put the dA, differential amount, put on it, bam. And because we already discussed that electric field is supposed to go out in all direction equally, so electric field is supposed to point out in the radial direction as well. So cool. So E dot dA is just going to be E dA cosine 0. And because if you want to do this in wherever you want, dA here, dA there, dA here, it doesn't matter. They're going to point out in the radial direction. And because electric field is supposed to point out equally in all direction as well, because we cannot tell which is up, which is down, which direction is left, right, there's no reason that there will be any particular direction that electric field is stronger than the other direction. So that means electric field is supposed to have equal magnitude in all directions as well. So that means E supposed to be just a constant value on this surface. I can pull it out from the integral. With me so far? And now what is the integral of the dA? Well, Ajahn, it's just a sum of those tiny pieces of dA, 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 dA throughout this sphere. So it's just going to be the surface area of this sphere. So everyone knows it's going to be 4 pi r squared. That's it, guys. This is the net flux throughout the surface of this sphere. Isn't that cool?
Okay.
But that's not it. Gauss's law say, if you can figure this out, it will be equal to the net amount of charge included in your Gaussian surface divided by epsilon naught, correct? So what I can do is I can just set this one to be equal to the amount of charge that's located inside this Gaussian surface. And I just divided by epsilon naught. How much charge in here, guys? Well, again, that's it. You only have plus Q in there. So all I need to do is just put plus Q in there. That's it. That's Gauss's law. But what is the application of the Gauss's law? Well, again, E is right here. 4 pi r squared is there. I'm just going to move 4 pi r squared to the other side. So I say E is 1 over 4 pi epsilon naught q over r squared. Does this one look familiar to you? Well, yeah, Ajahn, this is just the K. So it's the K q over r squared, exactly just like Coulomb's law. And that is the wow moments, guys. This is like a jaw-dropping moment here. Okay, that's it. That
Okay.
is the equivalence between Gauss's law and Coulomb's law. You can arrive at the same conclusion of the electric field at the distance r away from a charge to be some constant times the charge divided by the distance squared. And now this is the connection that I was talking about. See, the K that we introduced back in the Coulomb's law, the Coulomb's constant, can be represented in terms of another constant, which is the epsilon naught over here in the Gauss's law. They are exactly the same number. It's a K equal to 1 over 4 pi epsilon naught. So the epsilon naught that shows up in this Gauss's law over here, it's called permittivity of free space. So there's a name for it, but permittivity of, the reason it's free space because it's a blank, it's a vacuum. So that's why there's a naught sign over here. Okay. If it's epsilon, we'll talk about that for other material that is not blank space. But for now, it's just a vacuum. It's an epsilon naught. And that's it, guys. I just showed you we can arrive at the same conclusion as the Coulomb's law, but applying Gauss's law. And as I sort of like try to explain everything from scratch here, you see a little bit of the way that I'm doing is I have to come up with my own Gaussian surface. It's my own imagination. But the way that I select my surface is looking at the symmetry of the charge. So that's why in this summary of the application over here is like you try to use the symmetry, okay, to have to sort of like you pick you have to be clever picking the right shape of the surface. The reason that if you when you apply the symmetry of the system and you pick the surface to reflect that symmetry, it will make the electric field constant over the surface as we saw. So that make calculation a lot easier. All right. But anyway, that's just an idea that let's go through the problems examples is much better than just read you through this one and you still don't have a clue what is going on. But at least that's the idea that when you saw an example here and then you can trace back here like a guideline of how to apply Gauss's law. Okay, so don't worry too much about this page right here. Okay, so that's wow moments, guy. And this is like a very, very, I don't know, it's like a jaw dropping moment saying that, hey, we have another approach to what the electric field calculation. But the limitation of this one is just like, okay, John, it's like a high symmetric problem. Because if your charge distribution is not very symmetric, then you're not going to know what is the shape of the surface that you're supposed to use. So that's why I said, don't worry about the question in the exam because we can only apply this Gauss's law to just, a handful of system. I mean, not a lot, actually, just only some distribution of charge. So the application for our course here is going to be very limited. So you don't have to worry too much. And I'm going to show you with tons of examples that they all look the same. All right, guys. So that's what it is. Okay, so let's stop right here, take a break. Okay, I don't want to push too much. It's, I think it's very new and I think it's very, very weird. So I think it's just have it sit in your brain for 10 minutes. All right, and we'll come back. I will show you more how to apply Gauss's law in a different charge distribution. And I hope by the end of today's lecture, it will be quite straightforward to apply. Okay. All right, guys, take 10 And I'll see you at like 10:55. Yeah, sounds good. All right, guys, take 10. Right. So let's take a look at what else we can apply. Yeah, and just to make things a little bit simple, so we'll keep the spherical symmetry in place at this point. So that means we're still looking at the charge distribution that is distributed in the form of a sphere. So a point is a good, it's a spherical symmetry, right? When you have a point, you can imagine it's like a spherical ball that is super, super small. So that's why it still look like a sphere. Now we're gonna blow that charge up a little bit. Let's say if you have a solid sphere with with a size. So let's say the radius A, okay? So now it's not just like a point charge. It's a charge that get distributed across like a spherical ball of radius A, okay? So the way that we can define the distribution of charge around this, ball here is a three-dimensional ball. Now, you can do it through the charge density. Remember the density of charge that we were talking about back in the day of the electric field calculation? But at the time, it's a one dimension, right? So you can have lambda to be charge per length. Okay. So now in the three-dimensional, you can do a charge per volume. So that's in contrast. So rho is charge per volume. That's what we want. Okay. So that's fine. That's like a common concept of density is a charge per volume. But when you reduce the dimension down to only single dimension, so it turns into charge per length. But it's still the concept of density anyway. All right. So when you have this, then you can figure out the total amount of charge in this ball by just taking the charge density rho multiplied by the volume. So that's fine. So you can write this definition as the charge per volume. So every time that you want to get to the amount of charge, you can just say it's take the rho multiplied by the V. Either way you like, that's fine. Okay, so it's up to you. But now we know the relationship between density and the charge through the charge density. Now, let's calculate the electric field outside the sphere. So let's say you are standing at the location, let's say point P again, and the point P is at the distance r away from the center of this ball of charge. How much electric field at that point? All right, so I don't think anybody will get excited or anything anymore at this point. But then just get it done so we can do something else. All right, so think about it, guys. If you want to do this through Coulomb's law, but OMG, oh my God, that's going to be crazy. Why? Because if you want to go through Coulomb's law, what do? Well, I have to slide this into a tiny piece of charge. Let me call it a dq, but don't forget now it's a three-dimensional charge. So it's going to be like a tiny volume that contain the charge in there. And then you say, okay, John, what is the distance from this to that point P? And then you apply K tiny charge over R square, right? Well, John, that sounds okay. But think about it. If you have to do this in a three-dimensional space, oh my God, that's crazy. Because you have to have a slice of dq here, dq there, dq there. Okay, this is like my tiny cube there here. I mean, you have to do this dq throughout this spherical ball. And then who will have an ability to try to calculate the distance from all these tiny dq to point P? And then you have to do the integral. And the integral is going to be the triple integral because you're doing summation in 3D. Oh my God. Not good. All right. So that's not what we want to do. Okay. So Coulomb's law seems to be, well, I wouldn't say it's impossible. It can be done. Right. And actually, in the textbook, they pretty much they did it actually. Did it? All right. But anyway, we can do it. Mathematically, it's fine. It's just tedious, but it's doable. It's not impossible, but we don't want to do it. So how are we going to treat this problem then? So use symmetry. The ball is a spherical distributed charge on it, right? So that's fine. So the charge distributed equally uniformly across this ball. So it still pertain the spherical symmetry. So that lead us to, okay, Ajahn, let's visualize a sphere wrapping this ball, and we're going to name this Gaussian sphere or Gaussian surface in the shape of a spherical surface. Yeah. So it's a Gaussian sphere. And then try to calculate electric flux on this sphere, just like what we just did before the break. So the area on this one is the sphere. So it's the same thing. The area pieces, the tiny piece of area, the A still points in the radial direction all the time. So no matter where you look, the dA still point in the radial direction, radial direction, radial direction, no problem. And by the symmetry argument, electric fields supposed to point in all direction equally as well. There shouldn't have any particular direction that the electric field is stronger than the other. The sphere cannot even tell which one is up, which direction is down, left, right, north, south, none. They all look equally the same in space. So that suggests that the electric field supposed to point in the radially outward direction equally as well. Cool. Start to get a sense of what the Gauss's law is about. It's about, of course, first calculate flux throughout the imaginary Gaussian surface first. So what is the flux through our Gaussian surface? Bojan, same thing. E dot dA across this closed surface. And it's just a sphere. We're doing the same thing. But Ajahn, these two making 0-degree angle with each other. So the flux on this one is going to be, okay, let me write on the side here. It's going to be E dA cosine 0. And by the symmetry, electric field supposed to have the same magnitude in all direction. So I have only one left to do is just the integral of the dA across this sphere. But it's nothing more than just the surface of the Gaussian sphere itself, which is 4 pi r squared. So that's why I get here, right there. That is the net flux on this Gaussian sphere. That's it. I'm done with the flux calculation. Gauss's law say it's going to be equal to the charge included inside our Gaussian sphere divided by epsilon naught. How much charge you have here? Well, Ajahn, is the whole ball here. And we already said is, let's say if you already calculated to be total capital Q here, that is the amount of charge inside this sphere. You just plug that Q in there. And that's it, guys. You're done. You move 4 pi r squared to the right-hand side. Check. That's it.
Okay.
Isn't that cool? And it's much easier than applying Coulomb's law. You don't need Coulomb's law here. You get the electric fields at a distance r away from the center of the charged ball to be, but it looked the same as the Coulomb's law, but it's a guarantee from Gauss's law saying that it still look like kq over r squared. And you can re-express q in terms of the rho if you like. That's no big deal. So you can substitute q to be rho times the volume of the ball. That's fine. That's done. Cool. All right. I hope you start to see how to apply Gauss's law. It's not the same thing as Coulomb's law in the sense that you have to come up with your own Gaussian surface. And to pick a good shape to do the flux calculation, you apply the symmetry of the charge distribution. So that is the determining factor that which shape of the surface that you would like to pick, okay, to be your Gaussian surface. All right, try again. All right, it's more exciting. Bojan, okay, I got it. But it will be harder if you want to calculate electric field inside the ball. Whoa, this is more interesting then. Outside is fine. What about inside? So here's the next one. What about the electric field in a point inside this sphere? What's changed? Okay. So what's changed is it's going to be almost nothing. Why? I mean, it's still the same charge ball. It still have the spherical symmetry. So that means electric field is still supposed to point out in all direction, in the radial direction, same, no change. So symmetry of the problem does not change. You just change your location of your calculation. So that's why it suggests that you're supposed to pick a sphere to be your Gaussian surface anyway. You just reduce the size. So that's why you just now pick the different shape of the sphere to be included the location that you want to calculate the electric field. So let me call it point P again. So now point P is inside the ball, but you still create your imaginary Gaussian sphere anyway, but now it's inside the ball. So you calculate once again flux throughout this Gaussian sphere. So what is it? It's E dot dA total, I mean, across this Gaussian sphere. And look at this one closely. Nothing has changed. The dA on this one still points in the radial direction. Wherever dA you want is still dA. Whatever you want is still dA. And by the symmetry, electric field still in the radial direction, no change. What is going on here? Yeah, no change. Electric field, even though you don't know what the electric field is, but the direction of the electric field is supposed to be still in the radial direction due to the symmetry. No change. So that's it. So what you can see is it's going to be E dA cosine 0 under the integral. And once again, by the symmetry, electric field is supposed to have the same strength in all directions. So you can pull E out from the integral. You only left with just the integral of the dA, but the integral of the dA is nothing more than just the surface of this sphere 4 pi r squared, and that's it. You arrive at the net flux, which is exactly the same value as before, 4 pi r squared times E. And then you equate that to the charge that is inside your Gaussian surface divided by epsilon naught. This is where the things is now going to look different. Can you see how much charge you want to include here? You know that the total charge on this ball is capital Q, right? But that's not what you're going to put here anymore, because what you include now is going to be smaller. This is the only amount of charge that's being contained inside this closed surface, Gaussian sphere of us. Okay? So you have to calculate this much of charge, not the whole ball anymore. So how much is that? Well, John, that's easy. Because if you know the rho is the charge density. So you can figure out the, let me call it the Q included here. It's just going to be just the charge density multiplied by the volume, right? That's what we have. You get the rho, it's a density, multiplied by the volume, you get the charge back that you want. So you just take the volume of that small sphere there for third pi small r cube. That's it. That is the amount of charge that you need to include in here. That's how easy it is to apply Gauss's law. Whatever charge that stays outside of this sphere or Gaussian surface, you don't care. I don't want it. Okay?
Okay.
That's it, guys. Plug it in. So you have 4 pi r squared that you can move on the right-hand side as usual. So you can say E is 1 over 4 pi epsilon naught. It's there. R squared is there. You replace Q included by rho for third pi r cube for third. Okay, let me use the green here. Here. For third pi r cube times rho. That is the charge included. And that's it, guys. You are done. This is, I mean, you can cancel 4 pi if you want to make it nice and clean, but at least you get the end result. It's look like R rho over 3 epsilon naught, and you are done.
Okay. Okay.
Okay. All right. So that's it. When I said that's it means, well, it's new, but it seems to work. It not only seems to work, it's been working 400 years. So it works, but it's a different approach altogether. It doesn't look anything like Coulomb's law at all. And sometimes it's counterintuitive in the sense that you need some visualization in your head. It's kind of imaginary stuff, but it works. And what it tells you here is, hey, Ajahn, electric field inside the ball is linearly related, depending on the distance from the center of the ball. So what I'm saying over here is it means if you start at the center of the ball, the electric field will be zero. Of course, that makes sense because you're right at the center of the charge around you. So all electric field will cancel each other out to zero. But once you start walking out, electric field will get stronger and stronger, but in a linear fashion. So if I plot a curve of R and the electric field strength here, you start from zero and electric field is getting stronger, 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 stronger until you reach the surface of the ball with the radius capital R. And after that, it will follow 1 over R square function. So it means after that, it will just dying down. It's 1 over R square here and it's R here. There you go. So that is very good.
Okay.
We can get to this conclusion without doing like a triple integral if you were to do Coulomb's law. Is that better? All right. And this sort of like this examples of applying Gauss's law in this particular problems actually can actually, this is very good, go back to gravity, even though we didn't do this back in the day of gravity, but that's allow you to answer the questions if you imagine this ball of charge to be Earth. And let's assume that the mass of the Earth is uniformly distributed, which is not real. But just in case, imagine that if you have like a big circular, I mean spherical mass, like a star, and they like uniformly distributed on and on. Okay, let's assume that. So that means you can tell at the center of that star, you have zero gravity. And once you walk away from the center, the gravity increasing linearly. Once you reach the surface of that star and you're going above the ground, the gravity will drop 1 over R squared. See, so that's allow you to talk about gravity, just like when we started out with the gravity to talk about the electric field. So now you learn a little bit of Gauss's law, and then you can go back and talk about gravity as well, even though we don't do that. All right, anyway, it just try to make the analogy between the electric and gravitational field in line all the time. Okay, make things a little bit easier. All right, guys. Oh, there's a quick question about the final exams. Okay, guys. So I think we decided to be the last Sunday of the trimester. So it's going to be on 24th. Okay. So it's same format. On 24th of July, we're going to have our third exam, final exam. Yeah. Okay. All right, cool. All right, guys. So we want to do one more. Sounds good. And I think that's gonna be all I'm asking you for today's lecture. Okay, I think that's already heavy enough. I don't know. All right, but this one is already it's a very good applications and still within the spherical distribution, still not too difficult, and you can still try to apply Gauss's law. And once we're done with this, I think you have a very firm understanding of the Gauss's law. So tomorrow, which is our makeup, I can talk about the application that link to something that is realistic in our everyday life, is like a real devices and stuff like that. That's allow you to do something more. Okay, but that's for tomorrow's discussion. But for today, let's do one final question over here, guys. Okay, let's see if you can do it and see if that works. Okay, one more time. So we have done point charge, spherical ball outside and inside. Now let's turn our attention to spherical shell. So it's a shell now. It's not like a solid piece of like charge anymore. It's not like a thick solid piece. It's just like a thin shell. So question, same question. So let me draw that. There you go. Thin shell. So let's say you have charge distributed throughout this shell. They said Q uniformly over its surface. Find the electric field at the point outside and inside the shell. Same question, different shape, but still retain the spherical symmetry in the problem. And that lead you to, oh, Jan, if it's already spherical, your Gaussian surface is supposed to be spherical as well. What else could it be, right? Because the symmetry of the problem is still a spherical symmetry. So let's pick spherical surface to be our Gaussian surface, okay?
Okay.
All right, so let's apply the outside first. So if you are standing at the location here, let me call point P over here. You would like to calculate electric field at point P. What you need to do is you build a Gaussian surface that include point P in it. So your Gaussian surface, okay, let me try. Okay, I'm just gonna move here. Does it work? Does it work? Okay. All right, here we go. It's pretty close, pretty close. There you go. So my Gaussian surface is, of course, that bigger sphere right there. So what we want to do is we want to calculate flux on this surface. And every time that we learn here, it's just like, okay, dA is going to point in the radial direction everywhere, just like before. And because of the spherical symmetry, electric fields still point in the radial direction everywhere as well. No difference than before. So what we can do right away is try to calculate electric flux on this Gaussian surface of us. So it's going to be integral E dot dA on a closed surface, our Gaussian sphere. But then because E and dA are making 0-degree angle with each other, so it's going to be E dA cosine 0. And by the symmetry argument that electric field is supposed to point in all direction equally, that shouldn't have any particular direction that electric field is stronger than the other direction. Electric field is supposed to be constant throughout this Gaussian surface. So you are left with just E times the integral of the dA across this surface. And this is just the surface of our Gaussian sphere, where R is just the distance from the center of the shell to point P. So this is your fourth time seeing this, right? Okay, that's it done. That is your electric flux on this Gaussian sphere. You equate this to the charge that included inside this Gaussian surface divided by epsilon naught. How much charge should you put here? Bojan, the total charge on the shell is included. So that's it. You just put that in there. That's all you care about. And that's it. Move the 4 pi r square to the other side. You say electric field outside. So let me call out then. At point P is 1 over 4 pi epsilon naught Q over R squared, just like before.
Okay.
No change. So as long as you're still far away from the spherical shell, you will feel the electric field in the form of Coulomb's law, just like before. Still good. Still very nice. Okay, that's kind of neat. Okay, what about inside? Well, Jan, if you want to do the inside, there shouldn't be anything different. The only thing is you just reduce the size of your Gaussian surface to be somewhere smaller. So let's say if you try to figure out the electric field inside, so let me call this point Q then. So there's some point that, okay, let me point Q. Okay, so you do the exact same thing. So let, I think outside, this is part A. So part B, you do the flux calculation. So let me call this inside and so distinguish between these two problems here. So the flux for the inner sphere, still you want to still calculate E dot dA. But then you start to get sick of this. Ajan is a sphere, so dA point out in the radial direction everywhere, just like before. And due to the symmetry, electric field on this one supposed to point out in the radial direction. Doesn't really matter which direction you're talking about. So electric field and the dA is still pointing in the same direction. So the angle between them is still 0. So it's still E dA cosine 0. And by symmetry, again, electric field is supposed to have the same size, same magnitude in all directions. So E is supposed to be a constant that can be pulled out. Very good. And the integral of the dA is just surface of the Gaussian sphere 4 pi r squared. But now your r is just smaller than the radius of the spherical shell. That's all. But it's still 4 pi r squared anyway. That's it. And then you say equate that to the charge that is included in your Gaussian sphere divided by epsilon naught. Here comes the question. How much charge should you put there? What do you think? บอกอาจารย์ look inside. Hmm. How much charge inside this sphere? Well, aจารย์, there's none because the charge Q only located on the shell, right? Just on the shell, but nothing on this inner part of the shell. It's just a void, it's a blank, it's nothing. That's it, guys. I just put zero in there. And that lead you to electric field inside is zero. And you are.
Okay.
Is it good? So that's how easy it is to apply the Gauss's law. The concept is simple. You only take into account the charge that is included inside your Gaussian surface. Whatever that's outside, you don't care. Discard those. I mean, discard means you don't have to include it into your calculation. And actually, this particular calculation is kind of nice. It gives you first conclusion that you got here is no matter what you're talking about in terms of a point, a solid ball, or a spherical shell, as long as you stay away from it, the electric field that you experience will have the relationship with the distance, just like Coulomb's law, KQ over R squared, no matter what. So that's nice. But the thing that you can learn extra from this one, the second point from this example is, if you have a spherical shell and the shell is being charged and you are inside that shell, the electric field inside is nothing. So you can think of the shell to be the shield. Does that make sense? It's like you can shield yourself from the from the electric field by staying inside. So this is, well, this is not exactly the full explanation, but that is giving you a sense of every time that you in an elevator, your cell phone signal is down, right? I mean, try to make some connection here. But the idea is that because you can think of your cabin of the elevator is made out of metal, and sometimes you have some free charge lying around on and on, and you can imagine that you are probably shielded, and then that you get zero electric field inside, even though that's not the good explanation, because the cell phone signal using electromagnetic wave is not like a static electric field we're talking about. But anyway, that gives you a clue of that leads to the idea that's why electric fields cannot penetrate the metal container, is because a part of it is because of this one. So that's a good thing. Or if you think about it, if you stay inside a car which is made out of metal and then you get lightning strike, you should be safe inside the car as long as you don't have any part of your body touching the body of the car, because once you get lightning strike, bam, and then your car get charged, then you should still be okay in there.
Okay.
Yeah, don't try it. Okay. I mean, how to try it, right? I mean, what's the probability you're gonna get struck by a lightning? But anyway, the point is, I mean, in reality, it's more complicated, of course, because I mean, it's lightning. It's a very high voltage, so you ionize the air around you, so it's not like perfectly still. Everything is moving, it's dynamics, so it's not like perfectly fine. But in a very well set up environment, that there is an experiment that you can put like a cage, and then you charge the cage to a very high voltage, but everyone in the cage still safe. Yeah, that's the whole idea. So that was the uh, experiment to showcase that the electric field inside a charged cage is supposed to be zero. Yeah. And this we can sort of verify or prove by using Gauss's law. Sounds fun, guys? Yeah? Okay.
Okay.
All right, guys. So I think I would like to draw the end to our lecture just right here, because I think that is enough. And I think I already talked about the big concept, which is Gauss's law. And I think that's, serve our purpose for today's lecture here. All right. Sounds cool. All right, guys. So that is it for today. Thank you for sticking around. I'll see you guys in the next lecture. Bye bye.